Hi, can you hear me online?
Yeah.
Okay. Sorry, it started a bit late today, but we'll wait for a couple of minutes. In that time, let me discuss last time's puzzle. Did you try that telegraph cable puzzle and to find a solution for that? So we did the cases of two, three wires, six wires, and then we tried to generalize that to any number of triangular numbers, like any triangular number of wires. So like let us take the case of 10 wires. Okay. So 10 wires, and the problem is that there are these 10 wires coming out of this side and 10 from this side. And how to match them? That is the problem. And what is given to you is a circuit checker, like basically a box which has a bulb in it. And the question was, what is the least number of times you need to go back and forth between the two ends to figure out that which wire is connected to which other wire, right? So as we observed last time that because 10 is a triangular number, we have to use that somehow. And so what we thought, let us group the wires in the triangle, like 1, 2, 3, 4, like that. Okay. So now let me show the systematic way of doing that, which will solve the problem for us. So this is what we'll do. We'll arrange the wires in groups of one. So let me call that group one. So G1. So G1 has only one wire. Okay. Then the next group G2. G2 has two wires. Then G3 has three wires. And finally G4. Okay. So if I make this kind of grouping, and what will I do? I will connect all the wires in one group together. So I will join the ends of all these wires together. So I will join this, I will join this, I'll join this. Okay. And now when I go to the other end, what will happen? There right now I have 10 loose ends, and I don't know which wire is connected to which wire there. But as I start testing the pairs, right? Because I have this circuit tester which I can connect to any two pairs of wires. So what will happen if you do this testing? That there will be one wire which is not connected to anything else, right? And that wire has to be G1. So we will identify one wire. So what will happen is that we'll identify there is some one wire. Okay. So let me call this H1. Okay. So H1 is the group of wire which has only one pair. Now here it is obvious that this is going to be this wire. So there is no ambiguity. But then what will happen? Similarly, you will get a pair of wires such that they are connected to each other but to nothing else. So like that, you will be able to partition the 10 wires into groups, right? Groups of two wires which appear connected to each other. So that will be group H2. Then there will be a group H3 and finally group H4. Okay. And so what we know is that pairwise, like this group H3 corresponds to this G3 and H4 corresponds to G4. But we still don't know like what is the correspondence, that which of the wires inside that group correspond to that wire. And notice that up till now we have made only one trick. We started from left side and we went to R once. So far we have traveled only once from left to right. And now we are at right hand side. So now the question is, what should we do next? So do you observe anything about the way I have arranged those wires? Like they are triangular numbers, of course, but do you see how I arrange the points like in a triangular shape? Do you see that shape? And right now we are grouping them row wise. So can you think of some idea?
So can you share your screen because it's a bit blurred on camera?
We can use what?
Can you share your screen because it's a bit blurred on camera?
Oh, sorry, I forgot to do that. I'll do that. Sorry. Yeah, hopefully you can see now. So in fact, let me make it even more clearer by drawing this diagram in a slightly different way. So look at this arrangement. Do you see this grid? Oh, I made a mistake. It's double height. Okay, so do you see this grid of 10 squares? How I arrange it in a, no, like a staircase kind of a arrangement. And if I do the same arrangement on the right hand side, okay, so you can imagine that inside each of these squares, there is a dot which is corresponding to that particular wire. So like I've arranged the 10 ends of the wires in this grid fashion. And now what I'm saying is that the first row, I'm calling G1, right? So the first row is G1, G2, G3, and G4. And here we are calling the rows H1, H2, H3, and H4. So after the first connection is done and testing is done, we know that the row from G1 maps to the row H1 and G2 maps to H2, etc. But within that row, we don't know which wire goes to which wire. But so can you think of a solution here, that looking at this diagram, what should be the next step? And we are right now at the right hand side. See, is there anything special about rows and columns? Can we do the same thing column wise now? So what will happen? See, every point has a unique coordinate, right? A row and column. Where the row and column intersect, that will give me the unique location of that point. So what if we are sitting at right hand side? So what we'll do now is we'll connect the columns. So this wire will not be connected to anything else. We'll connect these two wires, these three wires, and these four wires. Okay. We'll connect these all of them. And so let us give the names to these columns. That's something I1, I2, I3, I4. Actually, we can come with a better name, but it's okay. So, and here let us call the column J1, J2, J3, J. So what will happen now? Now when you come to this side, there will be I1 corresponding to I1, which is the single wire, which is not connected to anything else. So where will that wire be? Firstly, it is in the row H4. So it is supposed to be in this group, right? G4. So out of the four wires in G4, there will be one wire which will not connect to anything else. So that has to be I1, right? So without loss of generality, let us say that wire is here. Or we can rearrange the wires within that group if we want, right? So that J1 is the wire which is connected to only I1. And we can keep going that way. So there will be some group of two wires which are only connected to each other and nothing else. And where will they be located? Within the role G3, G4. So for example, let us say that I find through testing that only these two wires are connected. Then can I uniquely establish the identity of both wires now? Because from the first step, I already knew that this end has to be from the third row. And now I also know that it has to be from the second column, right? And same for this. So like that, basically I'll keep getting, maybe for example, in this particular testing, I may get that this wire is alone, these two wires are connected to each other, then these three wires are connected to each other, and finally these four wires are connected to each other. So I'll get the groups of 1, 2, 3, 4 over here. And so now based on this diagram, can we uniquely identify all the correspondence here? Because every wire is in exactly one row and one column. And so now we can make the table which maps every wire from that side to this side. Okay. So I don't know if any of you actually have wires and this, electric circuit things at home. You can actually do this. I don't know, in labs, school labs, typically we have all these wires and bulbs and everything we have. So it's not too difficult. Maybe next time I'll actually do it because I have everything at home. I have all the bulbs, transistors, switches. So I'll actually get a cable next time with that's 15 wires. Let's not go beyond 15 wires. So that should take a lot of time. But actually have a bundle, a black cable, and because it will be opaque, you will not know which wire from this side correspond to which wire from this side. And I will have all of them the same color, all like 10, 15 white wires on this side and 15 white wires on this side. And let me see if you can actually try out this experiment and find out the mapping. Okay. But do you see how we are able to build a pattern? And one very important problem solving idea which is being used here is the simple fact that every wire has a unique coordinate, like one row and one column. Okay. So we are able to map the rows to the rows and the columns to the columns. That is the main idea here. Okay. So for those who joined just now online, just to quickly recap the solution that how we are solving the problem of that telegraph cable. So we are grouping the wires into rows and columns. Okay. So for example, here we are doing the case of 10 wires. So what we did is we created first this kind of a table where it is not a perfect square table, but it is a triangular table kind of, because we have a triangular number of wires, right? Where the first row has one wire, second row has two wires, three wires, and four wires. So in the first step, what we did, we already discussed this last time, that we'll connect the first wire to nothing, second wire to each other, third, all three wires together, and all four wires together. So we have this 1, 2, 3, 4 connection. Then we'll go to the other side and start testing. And through the testing, we'll find out that which is the wire which is not connected to anything else. So that has to land in the first row, H1. Then we'll get two wires which are connected to only each other. So they will land in the row H2. So like that, first we'll create these four rows. But within these rows, we still don't know that which wire out of H4, for example, corresponds to which wire of G4. So for that, what we said, let us now switch to column-wise operation. So on the right-hand side, we start connecting the wires column-wise. So we connected I1, we will not connect it to anything else. Then I2 will connect to each other, I3 and I4. And then we'll come to this side and then again start testing the same way. So just by changing the rows of the role of the row and the column, we can get the row coordinate and the column coordinate of all the wires. Okay. So anyway, this was just to discuss last time's puzzle, and we had a few other puzzles also, but I don't plan to cover them today. So what we'll start to do now is, as you know that Aditya is already conducting one lecture in another classroom. So what I'll plan to do is something in parallel to what he's doing. So because he's doing projective geometry, which is basically a study of various properties of points and lines under an operation called projection. So projection is what is called a geometric transformation. That you take a set of points, you do some operation, you get another set of point. That is what we call a transformation. So, but we have never discussed the entire theory of transformations as such. So let me start with that. Okay. So geometric transformation. Okay. And this will also be a very good opportunity for us to revise some of the things we did before, because what we'll find out is geometric transformations are going to be useful to solve many of the problems which you already know how to solve using traditional way. But with transformation, you get a completely unexpected new solution for those old problems. Okay. And I think to some extent, everybody is familiar with like homothety. Have everybody heard of this concept, homothety? Okay. So, and then what are the transformations that you already know? Can you list them for me? Apart from homothety, like rotation, reflection. Okay, you only know homothety. Okay. Okay, so then that is why this is a very systematic study is required, that will cover all the transformations that are there. So starting with what is a transformation? So transformation is simply a function from the plane to itself. Okay. So transformation simply takes all the points in the plane and applies some operation to them so that you get a new set of points. And typically, I should not say function, I'm more typically a bijection. Okay. That most typically the transformation we are talking about are not just any functions. See, I could have very boring function, which is that like in the xy coordinate, right? We have the origin, right? 0, 0. So consider this function f from r square to r square, such that for any point x comma y in my plane, I will map it to 0, 0. I'll just map all the points on the entire plane to the origin. That is also a function, but it's not a very useful function, right? So that we will not call that a transformation. Typically, transformations are bijections of some kind. So what is the simplest bijection that you can think of? Most trivial bijection. So firstly, what is a bijection? A function which has an inverse, right? So a function which is 1, 1 and onto. So there is one, when you're going from one set to itself, what is the most trivial bijection that you can think of? Doing nothing. Yeah, that's a function, right? So what is the function that for every point f of x comma y, f of x comma y is f of x comma y? So the function does absolutely nothing. But that's a function. So firstly, understand a function that does nothing is also a function. Again, not a very interesting function. But the beauty of this function, you can apply it as many times as you want. What is the year 2023? You can apply the function 2023 times, and you know what the output is going to be. So it has some nice properties, but on the whole, not interesting. So then we are ready to start asking that what are the kind of function that we are interested in, that what will help us. And we are talking about geometry. So we start to classify the functions in two categories. Okay. And so the first category we are going to talk about is called congruence transforms. Okay. So first category is what you call congruence transform. And why is it called congruence transform? Because what that transform guarantees is that a shape which is in some position currently, after the transformation, it goes to a new position, but it will remain congruent to the original position. Okay. So it preserves congruences. That is why it is called a congruence transform. So let me give an example. So the first transform which we call is translation. So translation means you shift the entire diagram, like shift of origin, you shift the entire diagram in some direction with a direction and magnitude, like a vector. So like if a point is over here, Okay. Then after the transformation, the point will go to new position P dash. And this vector is fixed. Like every point in the whole plane will be shifted with the same vector. So if you want to formally state it in terms of function, like so let some a comma b be of vector. So a comma b is a pair of numbers which represent the x and y coordinate changes. So the function is defined as f of x comma y. Okay. So point x comma y goes to x plus a comma y plus b. In other words, we are adding that a and b as coordinates to the x and y. Right. So in like to show a diagram, what it will look like is if suppose this is my a comma b. Okay. So this is the point a comma b. So my sorry vector is slightly tilted, but it's okay. So what will happen? Any point in the plane you take, right? Suppose there is a point over here, and to this point you are going to apply this function. So what will happen? Like geometrically speaking, what do you think will the diagram look like? If I call this point O and this point, I don't know, T for transform. So you see that I will get a parallelogram because if I change the coordinate of P with exactly that A comma B, right? So what does that mean? That I will, this is the X coordinate, this is A and this is B. So I'll apply the same operation to the point P, right? So I'll shift the point P to the right by A and up by B. Okay. So this is the point P dash. And you see, I will get a parallelogram basically because these two lines are equal and parallel. Okay. When I don't know if you already studied vector addition. So you see, this is exactly addition of two vectors. Like my first vector is this OT and the second vector is OP. So do you know what happens when you add vectors? You use the parallelogram rule to complete the addition, right? So this is exactly like that. Okay. But the important thing is that this A and B are fixed, but the point itself can vary. So this point P is over here. If I take another point Q somewhere over here, let's say, then for the point Q also, I'll apply the same operation. So Q will go to new position Q dash. So every point in the plane will go to new position. You can imagine that I pick up the whole plane, move the entire plane to the new position. So all the objects will go in that way. Okay. And now do you see why this is called a congruence transform? Because if I started with the segment PQ and I'm ending with the segment P dash Q dash, do you see that they are congruent to each other? So PQ is congruent to P dash Q. Segment PQ is congruent to segment P dash Q dash. And this will happen not only for one segment, you can take any object. It is like common sense, right? If you take any object and you pick it up and place it somewhere else, that is not going to change its congruence. All the angles, everything will be preserved. Okay, so this is called translation. Okay, just to illustrate again this point that you can make any change you want. So let us say, for example, I have a triangle here. Okay, some triangle ABC. And to this, I apply a translation to some particular vector. So now there are several ways of denoting the vector. You can either denote the two endpoints of the vector, or you can denote it as magnitude and direction, uh, depending on whatever convention you want. Right now, I've just denoted like an arrow. Okay. So if I apply this arrow to this triangle ABC, you can see what will happen, right? All the points will get translated that way. So you'll get a new, so we will get something like this. Okay. Okay. And you see that the A dash B dash C dash is similar to congruent to ABC, right? That is why this is called a congruence transformation, where triangle A dash B dash C dash is congruent to triangle ABC. And not only is the triangle congruent, see everything inside the triangle will also be congruent. Like if you take the centroid of triangle ABC, where will the centroid of triangle ABC go? Under this operation, it has to go to the centroid of A dash B dash C dash, right? Because the all the properties get carried over. That is the most useful thing about this. So I can guarantee it the centroid goes to the centroid, the orthocenter goes to the orthocenter, 9-point circle goes to 9-point circle, and anything, anything and everything goes that way. Okay, so we need to think about what is the use of this. That how will this operation help us in any way? So I'll share one problem with you. So you need to connect two cities. Okay, there is city A and city B. Okay, these are two cities, and you need to connect them. And you are the engineer, so you have to build the road which will connect from A to B. So normally speaking, what is the shortest path that you will construct? Direct segment, right? That is the shortest path. The difficulty is that there is a river in between. Okay, so there is a river like this, okay, of fixed width. So this width is fixed of some width d. Okay, so this river of width d, and whatever path you construct, you have to construct a bridge on the river. So your path will look something like this. And typically, because the material cost is so much, you want to build the shortest bridge possible. And so, what will the shortest bridge possible look like? It will be perpendicular, right? I mean, you will not construct a bridge like this. You will always construct a bridge like this. The only question is where to construct the bridge. So you could construct it here, you could construct it here, here. Anywhere you construct, I mean, the two endpoints of the bridge, we understand that there will be straight lines. So for example, if you construct the bridge here, it will be like this, right? So this will be the path you will make from A to B. Or if you construct it here, the path will be like this. So you have the choice to decide where you want to construct the bridge. But what is the goal? The total travel distance from A to B has to be as small as possible. You want to join AB? Okay. And so so you want to construct the bridge here, here or here? Midpoint of AB, here and here. Okay, but what is the proof of that? That this is the shortest, or this is your guess? See, it's a big project. It's going to cost 100,000 crore rupees. And you cannot just say, go to the government, I took the midpoint of AB, and that is why I'm constructing it there. There has to be some reason, right? So think about it. Online, did you understand the question? That you need to decide where you want to construct the bridge so that the total travel distance between A and B is as small as possible. Let me just draw the diagram again. Because so A is here, B is here. There is a river which is of it is a basically two parallel lines you can say, okay, of length D, and you need to find the position of. So let us call the endpoints of the bridge at P and Q. So find the position of segment PQ. What's that? The total distance. So AP plus PQ plus QB is millimeter. And actually, if you think out of that, see, PQ will always be of fixed length D, right? Because that is perpendicular. So actually speaking, we have to optimize AP plus PB. Like PQ will automatically be as a constant. So PQ we don't have to worry about. Okay, anybody have a solution? So let me remind you of a problem which you already know very well, which is also for going from A to B and finding the shortest distance. Remember that problem? What is that problem? The farmer and the river, right? Everybody remembers that problem. So what was the key idea that did we do that to that problem to solve that? If you remember, what is the solution of that problem? So there is a line and the 2 points, right? A and B, and you need to collect water from that river and then go to point B. So what did we do to solve that problem? If you remember. We have
Yeah,
to do
we took
something.
the reflection of that
We took
point.
the reflection of 1 point, right? We took the reflection of, let's say, point B. And so what is the purpose of that reflection? What did that achieve? That, it was a kind of TKP. We already know that the 2 points, we know the shortest path is joining a straight line. So we converted that problem into that kind of problem, right? So just to quickly recap what we are talking about. So the problem was like this: you from need to A to B, you need to go and take the shortest path that will visit the river. So as what Ruhan is reminding us, that we take the reflection of the point B to get a point B dash. And what we observed is that any path that goes from A to B, right, from the river, like this one, like suppose this is the point P we are saying. So AP plus PB is the same as AP plus PB dash, right? And so now the problem is reduced to finding the shortest path from A to B dash. And that we already know how to do, that is the straight line. And so that finished the problem. So the key idea was converting the, what we can say, broken line segment into a continuous line segment. So we have to do the same thing here. But there it was reflection. Here, what will the operation be? Obviously, I give this example after translation, so it has to be translation. But translation of what? Can you think of the right translation
The
that will
translation
convert
of 1 point across the river,
across the river? What do you mean exactly by that?
as in parallel to the river, sorry.
Okay, so can you? Yeah, I think the idea is correct. But can you specify which point I should translate and how?
Sir, we should translate point A parallel to the river such that AB becomes a straight line perpendicular to the river.
Perpendicular to the river. No, I don't know what you mean by that. But this is what I will suggest. Uh, think of it this way. See, we are going to do three roads, right? AP, PQ, QB. What if I did the same road but in different order? You can imagine them like pieces of a, I don't know, some puzzle game. You can rearrange the pieces. What if you do PQ first? What does that mean? What about this transformation? And let us do it for B, just to keep it consistent. There also we did not change A, we changed B, right? So let us change B here. Okay. So in that sense, what if you do PQ last? So this is where our original position B is. What I'm saying is, why don't I translate B upwards by PQ? So consider this point B dash such that this is parallel and equal to this. Okay, so I'm applying the translation. So, and again, this is important. How do you write this kind of a thing in an exam? So let me write it in the proper language. So to write it, we'll say that consider the translation B or actually let the translation of so whenever we are applying a transformation, we have to clearly say what are the parameters that need to be supplied. I cannot just by translation, this object is related to that object. I have to say what translation. And so for a translation, the vector has to be specified. That what is the vector I am applying here? So the vector here is the QP. So in other words, starting from Q and going to P. What if I do the same operation starting from B and going to B dash? So what will happen now in this diagram? Can you observe anything? That so therefore BB dash is equal and parallel to QP, right? And the most important thing about this is that we actually don't know where PQ is to be chosen, right? PQ can be anywhere on this line. We have to find out the position of PQ. But does this vector change? See, this is just this perpendicular line, right? So no matter where you place PQ, it is going to be the same vector. All of these are parallel, right? So I could choose any of them and apply the transformation. I'll get the same output. Okay. So strictly speaking, I should not even say QP because there the problem is P itself is a variable point. Maybe I should, to be absolutely clear, I should take a separate vector on the side if I call that Q0, P0, right? And I should refer to that. So that is nothing to do with the path which we want to modify. But I mean, that is a small technicality just for clarity. But the main point is that this B dash is parallel and equal to PQ. So what? How does that help us to solve the problem? P B dash will be to QB, correct? Because it's a parallelogram, right? So PQB B dash is a parallelogram, correct? Therefore, PQB is equal to PB dash. And so what was the original path that we wanted to minimize, and how is that changed now? AP plus PB dash plus B dash. Yes, correct. So the original distance we wanted to minimize was AP plus PQ plus QB. And now I'm saying what is the new distance? So now you go from A to P, then from P to B dash, and finally from B dash to B. But do we all agree that these two distances are equal in length? Because all you have done is rearranged actually. So AP is still AP, PQ it will be equal to B dash B, and PB dash will be equal to QB. So all I've done is rearrange the paths. I mean, just to make it even clearer in my diagram, I can draw this line segment with blue color. Okay, so you see what I was saying about rearranging the paths. Originally, the order was white, blue, yellow. First the white segment, then the blue segment, then the yellow segment. Now the order is white, yellow, blue. But the distance does not change, right? And the important thing is this point B dash is fixed, right? And so, B dash is fixed. Is this quantity also fixed? B dash B, this distance also fixed. So now what is it that we want to minimize? AP plus PB dash, right? I only want to minimize this quantity. And how do we do that? Straight line. Correct. So basically the construction is you draw the straight line from A to B dash, right? I find this updated version a little bit harder to deal with. Every time this bar goes away, is there any way to lock it? So draw the straight line from A to B dash, and wherever that straight line cuts the river, that has to be the point P. And again, we have to complete the proof that we did this construct. So let me call this point P1 and Q1. Okay. So our claim is that this point P1, Q1 gives us the shortest path. Okay, but how will you write the proof of that? So construct AB dash point P1. So claim is that our claim is that A P1 Q1 B, this is the shortest path. Okay, let me write it here itself because it's not a very long proof actually. So to prove that this A P1 Q1 B is the shortest path, basically what I need to show is that it is shorter than any other path. So we need to prove that A P1 plus P1 Q1 plus Q1 B is smaller than or equal to any other path. So here it is, for example, AP plus PQ plus Q. So understand the setup that this P1 Q1 are fixed points and PQ can be any points on the line, but I have to show that no matter where I choose the PQ, I will still get a distance which is greater than P1 Q1. Okay, so how will you simplify this? What we need to prove?
AB is PB dash is greater than AB dash.
Correct.
So hence intersection point, AB dash will be shortest distance
Yes.
and BB dash is constant.
Yes. Correct.
So AB dash plus B dash will be B dash.
Yes. Correct. So I have drawn A. This we don't require AB dash. This point is not required. PQ, that is from the previous box. Okay, so this is how we can rewrite this, right? We want to prove that this AP1 plus P1 Q1 plus Q1 B is smaller than AP plus PQ plus QB. Out of that, first thing we notice is that P1 Q1 and PQ are equal, right? So we can cancel them out. We don't need to keep writing them. So therefore, it is enough to prove that AP1 plus Q1B is less than equal to AP plus QB. And now because of the way we are constructed, we know that Q1B is the same as P1B dash, right? So I can replace this term by P1B dash. And same in the same way, I can replace the term QB by PB dash. Understand, I can do this because actually there are two parallelograms in the diagram. Do you see both parallelograms? So basically BB dash is equivalent parallel to P1 Q1. That gives me one parallelogram. And BB dash is also equivalent parallel to PQ. So that gives me the second parallelogram. And so they are done, right? Because now if you see left hand side, AP1 plus P1B dash is just a straight line. So that is equal to AB dash. And so actually what we have is a triangle inequality, right? AB dash is less than equal to, which is true because of triangle inequality. And again, equality only when P lies on that segment. Okay. Any doubts in what we did? So first understand the visual intuition, like completing the proof is just the details, but first the diagram should be clear in your mind that what we did, how this translation helped us to solve the problem. The best way to describe it, I would say we are just rearranging the order of the roads. So instead of doing, so first we did AP, then PQ and QB, we are doing the same thing in different order. We are first doing AP, PB dash, and then B dash B. So just changing the order, we are able to solve the problem. Or I will describe another, very creative way of, solving this problem. It's a very creative way. Suppose you are Marvel Universe, Thanos, some powerful entity, who can move planets or lands. So what you will do? So imagine these are like two continents, right? That continent and this continent. Actually, need to draw the diagram for that. So the point is that this point A. So this is one land mass. Okay, this is maybe one continent, and this is another continent. So these are the two separate pieces of land. Okay, and your point B is located here. So what Thanos will do, he will move this temporarily, he will close the river by moving this whole landmass down. Okay, so he'll close this gap by moving this whole landmass down, or other way around. Let us say we'll move the whole landmass up from the bottom. So this entire piece of land, he just picks up and places it such that that river closes up. Okay, so this whole block shifts up by that, whatever is the distance D. So now the diagram looks like this. The point B has gone to B dash and the river is no longer present. So we have to continuous land. There is no river in between. And now what is the shortest distance from A to B dash? The straight line. So you close the gap, draw the shortest distance, and now again you are Thanos, so you can move that back, right? And so when you move it back, what will happen? This part will remain exactly as it is. This segment will shift down, and you got your path. You still need to construct the bridge, but you found the shortest path, right? So Thanos solution. But that is exactly what we are doing here. In a way, we are ignoring the river. But when we ignore the river, we have to compensate for that by shifting the position. So we are no longer trying to reach B, we are trying to reach B dash, as if the river is not present at all. Okay, so I hope this intuition is clear. The completing the proof is of course important, but I think we can manage that. Okay, I'll just give a couple of minutes to write anything you want. Okay, maybe one more application of translation that comes more directly from our geometry, that what we have studied so far. This is a very interesting observation. So we all know about 9-point circle, triangle, all those things. The question is, can a quadrilateral also have a 9-point circle? Huh? We know triangle has a 9-point circle. What if I tell you a quadrilateral can have something like a 9-point circle? Not exactly, but something interesting like that happens for a quadrilateral also. But not any quadrilateral. Actually, I need a cyclic quadrilateral. Okay. So this is the diagram. I will take. Sorry, I was still. There. So I'll start with a circle and I'll take 4 points on the circle. And if I even join the diagonals, okay. So let us start with some observations about this diagram. And sorry, let me not label them as A, B, C, D because that is not bringing out the symmetry of the diagram. We should call them maybe A1, A2, A3, A4. Okay. Does it matter? So we have 4 points. How many triangles will get formed using these 4 points as vertices? Huh? Four points in front of triangle. 4 choose 3, no? 4 triangles. 4, no? Basically, you will leave one point out and remaining 3 points will form a triangle. So like that, you will get 4 triangles. And what will the 4 triangles have? Each of them will have its own orthocenter, for example. So what about that orthocenter? Start with consider the orthocenters of let us say A1, A2, A3. And I will denote that by H4. By H4 because 4 is the number which is not occurring. So the orthocenter of A1, A2, A3 I will say is H4. And can I label all the orthocenters that way? So then the orthocenter of triangle A2, A3, A4 H1, right? So let us have only 2 orthocenters to begin with, H4 and H1. And now, can you construct them and tell me if there is anything interesting about them? Yes, Rohan.
Yes, sir. Sir, E1, H4, H1, and E4 is a parallelogram.
Yes, correct. And why?
Sir, because even H4 is twice the distance of O from A to A3,
Yes.
and which is half the distance of E4 H1. So
Yes.
even H4 and E4 H1 are congruent, and since they are perpendicular from E1 and E4 on the same line, they are also parallel.
Yes, correct. So the key point to understand what Rohan is saying is that how do you construct the orthocenter? See, at this point, you should have multiple ways of constructing orthocenter. It should not be that every time you want to construct the orthocenter, what you do is you join the altitudes. We know so many properties of orthocenter that we can come up with the right characterization based on the problem. So all of us, do we know this property that if I take O as the center of my circle and I draw this altitude, right? Okay, O does not look like the center. Maybe some other issue. So from O, if I drop this perpendicular, yeah, it is bisect, but what is the relation with the orthocenter? Let us say triangle A1, A2, A3. What is the orthocenter have to do with this? If I call this midpoint M23, midpoint of so what is the relation of this with the orthocenter of this is the orthocenter H4. Then do you know that A1 H4 is parallel to this and twice the distance, right? Because I mean the standard property. If I join these two, then this is the centroid, right? So through the centroid, if I apply homothency, this OM2 M3 will become that A1 H4. So therefore, A1 H4 is parallel to OM2 3 and twice the distance, right? It's parallel and twice of that distance. Right? Let me erase all this. And won't the same thing happen for A1 also, H1 also? Because here also what I'll get is, so here this, because it's an obtuse triangle, so the orthocenter is going outside the diagram, right? Actually, my diagram is not very good. I this should appear double. It is not appearing double. Let me draw it even further down. Yeah, maybe H4 is somewhere over here. And H1 will also be so severely shifted down. Okay, so this is H4 and H1. And what I am saying is that A1 H4 is parallel and twice of OM23. And similarly, A4 H1 is also parallel to OM23 and twice of OM23. And so therefore, and in the diagram also it looks like that A1 H4 and A4 H1 are themselves equal and parallel. Because why? They are both parallel to this segment and twice the distance. So therefore, they will themselves form a parallelogram. And therefore, what can you say about the line H1 H4? Because they form a parallelogram, H1 H4 is also equal and parallel to A1 A4. Right? So do you see that we are talking about translation only here? We are taking A1 A4 segment and we are translating it downward through the vector which is twice of OM23. So on the, if I have to describe the same diagram through the language of translation, I can say that translation of segment A1 A4 through vector 2 times M23. Understand this notation? I'm taking the vector OM23 and I'm doubling it. So this is the original vector, but I'm taking the vector of twice the distance. And that is the vector. If I apply that to A1, I will get H4, and to A4, I will get H1. Okay, do you see this in the diagram that this red vector is, if I take the line segment A1, A4, pick it up and apply this red arrow, it will go to H4, A1. So I want to say the translation. So the translation of this segment, to understand what is the concept, the starting object is A1, A4. The operation being done is the translation, and the final object is the new segment. And is there anything special about H1, H4? I could do the same thing to every pair of 2 points, right? And so what happens is that, let me actually show this in GeoGebra. One pair at a time, every pair of segments okay, so let me start the circle and ignore the notation. I mean, that will just. And that let me do slightly smaller. So these points C, D, E, F are our original 4 points. Okay. Maybe something like this. Okay. And now we are going to construct the orthocenter of this, right? And so, I mean, I can drop the perpendiculars to construct the orthocenter, or I can take the midpoints of the sides. So G is the midpoint of this side, and yeah. And just to illustrate that how the orthocenter is related to this. And by the way, if you notice in GeoGebra, we have this whole transform section. This is all geometric transformation we are going to do at some point. And so the first one is translate. So what I have to say? Translate. And see, it is giving the prompt that select the object to translate. What is the original object and what is the vector? So I am going to select the point C as the original object. And I have to take, okay, I need to first construct the 2G segment. Let me do that first. Best way to do that is again through operation actually. So if I reflect A in point G, so this A, you see that this A dash is the vector of twice the distance of AG, okay? Because G is the midpoint of that. And so if I translate my C to this vector, so you see this A dash is the vector through which I'm translating C to go to C dash. And you see that C dash looks like the orthocenter of the triangle CDE. And if I do the same thing to this point also, F to the same operation. So F dash. So CF became C dash F dash. Okay. And so I obtained the orthocenters of 2 triangles. Now let me obtain the orthocenters of remaining 2 triangles. So which are the remaining 2 triangles? CDF and CEF. Right. So for that, let me take the midpoint of these 2 sides. Okay. So AH. So what will happen again? AH is the perpendicular from the center to one side. So twice of AH will be the vector from D to that orthocenter and E to that orthocenter. So again, let me construct the okay. So I've doubled the AH to A1 dash. So that is the vector, and I'm going to apply that vector to point D and E. Okay, so I got the point D dash. So D dash is the orthocenter of CDF, and in the same way, I can translate E to E dash. So E dash is the orthocenter of CEF. Okay, so this C dash, D dash, E dash, F dash, these are the 4 orthocenters of those 4 triangles. And now if I join them, do you observe anything about this? So look at the original quadrilateral, which is this, right? Let me color. So let me color the original quadrilateral with one color. And let me color the new quadrilateral. So I'm joining the orthocenters to create a new quadrilateral. Do you see that? Because what is happening one pair at a time, right? See, segment CF is equal and parallel to C dash F dash. And that will happen for every pair of points, right? CD is equal and parallel to F dash C dash. And like that. And like if I move the diagram, obviously, the 2 quadrilaterals always remain equal or congruent to each other. Not only are they congruent, you see they are like a reflection of each other. It's like a mirror image of kind. Okay. And why are they the mirror image? Because going back to the diagram briefly of what we were showing on the board. Okay. So we agreed that look at this parallelogram A1, A4, H1, H4. Okay, this is a parallelogram, and what do the diagonals of parallelogram do? They bisect each other, right? So A1, H4, sorry, A1, H1, and A4, H4. These are the diagonals, right? This is the first diagonal of my parallelogram, and this is the second diagonal. Okay, and so this point is the midpoint of both segments, A1, A1, and H4, A4, H. But there is nothing special in the numbers 1 and 4. I could choose the numbers 1 and 3, 1 and 2. Any pair of numbers I'll get that those lines, those segments have the same midpoint. So what does that mean? That all four segments have the same midpoint. So A1, H1, A2, H2, A3, H3, and A4, H4. All four of them will have the same midpoint. And so actually what we thought was surprising, actually we are reflecting the original quadrilateral in that common midpoint to get a new quadrilateral. And so under that operation, there is obvious that it is going to remain congruent to itself. Okay. So just to show that again in the diagram, what I'm saying is that look at the midpoint of, so take triangle CDE for example. So CDE, the midpoint of CDE is C. Sorry, the orthocenter of CDE is C, right? And the remaining fourth point which was not used was F, right? So look at the midpoint of CF. Okay. Let me just draw the midpoint. I will not draw the line segment. So my claim is that this I is the midpoint of all these pairs, not just CF. You see that I is also the midpoint of D dash E. I is also midpoint of DE dash. I is also midpoint of CF dash. So all four of them are passing through the same point. Let me just move it a little bit. Okay, so therefore all those lines pass through I. And we don't know much about complex numbers yet, but eventually you will learn that you can say that this I is the orthocenter of this cyclic quadrilateral. Okay, so a cyclic quadrilateral also has an orthocenter, and to construct that orthocenter, this is how you do it. That you first construct the orthocenter of each individual triangles, and you construct that quadrilateral, and the point of reflection around which that original quadrilateral goes to the new one, that is the orthocenter. So again, let me just join these segments to make it clear. So look at this. I'm joining all these segments and they're all passing through I. It's a very complicated diagram, but hopefully you can follow. Okay. So this is what we call a orthocenter of a cyclic quadrilateral. Okay. So the midpoint of, so I would say the common midpoint of segments E1, H1, Okay. And not only that, this point is very special because so this all depends on how much you remember like 9-point circle configuration, all those things. This yellow point, right? Let me denote it by some other capital H, okay? Which I'm calling the orthocenter of my triangle, slightly quadrilateral. So understand, this is the midpoint of this segment, right? H is the midpoint of H4, A4. And but what is H4? H4 is the orthocenter of one triangle. H4 is the orthocenter of triangle A1, A2, A3. And A4 is a point on the circle. And so some of you said that you know homothety. What homothety do you know? Do you know the homothety that connects the 9-point circle to the circumcircle? That H is the orthocenter of your triangle is the point through which if you apply homothety of ratio 2:1, the 9-point circle becomes the circumcircle and vice versa. Right? And under that homothety, every point goes to that corresponding point, right? And the reverse is also true. If you start with a point on the circumcircle and you apply homothety of ratio half, you get a point on the 9-point circle. And so is A4 a point on the circumcircle? And now if you apply homothety of 1/2 with this as the center, where do you go? No, in this diagram, where are you going? The homothety with this as the center and ratio half will take A4 where? To H, right? So H has to lie on the 9-point circle. So actually all 4 triangles are concurrent. The 9-point circle goes through H. So the 9-point circles of all the 4 triangles 9-point circles of all 4 triangles. Which are the 4 triangles? A1, A2, A3. So this is a very rare occurrence that there are 4 circles which are all passing through the same point. And I mean not any 4 circles, the 9-point circles. Okay, did you understand the reason why? That again, just to go back to the diagram, that let me just draw one 9-point circle. I will not draw all 4 of them because then that would make the diagram very complicated. Let me draw the 9-point circle of, and let me erase this. Yeah. Let me just construct the midpoint of one. Like let me construct the midpoint of C here. Okay, so this is the point I. And what we are saying is that C is the orthocenter of triangle CDE, and we are applying the homothety with ratio half to this circle. And so under that ratio, F is going to go to I, and we know the 9 points, the circumcircle will go to the 9-point circle of triangle CDE, and therefore I has to lie on that circle. So to prove this, let us construct the 9-point circle actually. So I have marked the midpoints of the 3 sides, G, J, and K. So if I draw the circle passing through these 3 points, that should be the 9-point circle. And let us see whether it actually goes through the. So, okay, so this is the 9-point circle of triangle CDE. And yeah, it looks like it is going through I, but let me just clean up the diagram a little bit. Yeah, let me, so you see, no matter how I change the diagram, that I is always lying on that circle. And same thing will happen with all the other 9-point circles. So there are 4 9-point circles which are all passing through I. And once you go home, actually construct this diagram very nicely with ruler and compass. Take a circle, take a cyclic quadrilateral, construct all the 4 9-point circles, and verify that they are all passing through I. Not only that, so do you know Simpson's line? Simpson line, what do you mean by Simpson line? If you take a point on the circle and you draw perpendiculars, they are collinear, right? So let us do that. Because we have 4 points on the circle, right? C, D, E, F. So what can I do? I take one triangle and the fourth point. I can keep doing that, right? One triangle and fourth point. So which triangle do you want to take? Let us take triangle CDE only because we are working with that. And the fourth point is F. Okay. So I've just completed the lines because the altitudes may go outside sometimes. And so from the point F, I'm going to draw altitudes to these sides. And what do you think will happen? So I need to construct only 2 altitudes. I don't need to construct 3, right? I need to, and where I take the fit of the altitude. So this point L and M. And if I join them, I'll get the Simpson line. The Simpson line is also passing through I. And that will happen to all the 4 Simpson lines. So this point I, or in our notation, the orthocenter. So this is your homework. I will not prove it right now, but it is for you to prove this homework that the 9-point circles of all the 4 triangles are concurrent at H, and the Simpson line of, let's say, point A1 with respect to the other 2 triangles A2, A3, A4. A2 with respect to like that, right? A3, A4, A1, etc. So all 4 Simpson line also pass through it. So there are total 8 objects passing through H, 4 circles and 4 Simpson lines. So this is not the 8-point circle actually. There's a different 8-point circle. Actually, in the quadrilateral, we don't get a 9-point circle. We get an 8-point circle. Okay, so it is a slightly different theory, but we are not able to reach that yet today. Yeah, but I think we have spent a lot of time on this configuration, so we can move on. But like, pay attention to this, that, and all we have done is taken a cyclic quadrilateral. At the end of it, it is not like some special diagram. Any 4 points on a circle, and you'll get various triangles. And for all those triangles, you have to construct the orthocenter. Same thing is true for other points also. Take the 9-point centers of those 4 triangles. Take the centroids of all those 4 triangles. All of them will be rated with very similar properties. Okay. So just to show the diagram one last time. Okay. And actually, we never completed a diagram on here. So let me just do that. So this blue quadrilateral is the congruent to the original A1, A2, A3, A4, and it is a reflection in that orthocenter. Okay. So let us finish with one last problem, again using translation as a main idea. So what you need to do is this. There is a circle given. There is a segment given here. And there is another chord here given. And you are given some length 8. Okay. We don't know. what is that length A, or rather we know that length A, but so what we need to construct is a point on this circle. So understand what are the fixed objects. So PQ are fixed. This, let us call it RS. This is also fixed. Only this point is variable. Okay, so let me call it point X. So X is the variable point. And as the point X varies, what will happen? These points will also vary, right? Like if you change the position of point X, if you take the point X over here, then these points will also change. And so this line segment also keeps changing. Your task is to find the position of the point X such that this chord is of length A. This line segment is of length A. Okay. So find the position of arc RS. Well, let me say D. So D is whatever some distance given to you, and you want to find the position of X such that this YZ is of that length D. So when this point X approaches one of the endpoints, like when it comes very close to R or when it comes very close to S, what will happen? This Y and Z will be very close, right? So basically that segment is becoming smaller and smaller. So at one end of the spectrum, like when X is very close to R, that segment will be almost non-existent. And same on the other side. But somewhere in between, there will be one position or maybe more positions where that length of that chord is exactly D. And you have to find that position. And when I say find, I mean the ruler and compass construction. So in a question like this, where some things are moving, what is the most important thing to understand? What is not changing? Because whatever is not changing is going to be the key to our solution. Just as if you go back to that river problem, what was not changing is the fact that that vector from one bank of the river to the other was always fixed, right? That vertical vector d, and that is what we could use to finish the problem. So in the same way, what is not changing here? You see this vector yz is not changing. The points y and z themselves may change, but wherever that point x is going to be, we don't know where the point x is right now, but wherever it is, do we know already that what this yz vector is going to be, and what is the magnitude of, what is the length of that vector t, and what is the direction it will be parallel to rs, right? So that information we have, that we have this vector available to us of length d and parallel to rs. What else is not changing? The point x is going on this circle. So what will happen?
The angle PXQ is not changing.
This angle also not changing, correct? This angle is also fixed. So this angle is fixed. This vector is fixed. So, so what? And remember, when you are applying the translation, you see in multiple examples by now, right? When you create translation, you create parallelograms. You get parallel lines. And so under parallel lines, we have so many angles that can be created. And so same as what we did the river problem, you can think of it as I am going from point P to Y to Z to Q. Can I change the order? if I think of these as three different vectors, right? So going from P to Y is one vector, then Y to Z is the second vector, and Z to Q is the third vector. Can I change the order of these vectors? I hope everybody understand that just as three numbers can be added in any order to get the same final result, three vectors can also be combined in any order, you still reach the same final. So how will you rearrange these three vectors? Why don't we do this? Instead of doing Py, Yz, Zq in that order, first I go from P to Y and I flip the order of the red and the yellow vector. So I will first do Zq and then Yz. So what will that diagram look like? From Y, how will I travel? Parallel to Zq, like this, and then like this. Okay. So in other words, if I call this point Q dash, Q dash Q is equal and parallel to Yz, right? Q dash Q. And now the key question, we still don't know where Yz is, right? Because the point X is varying, so Y and Z are themselves varying. So we don't know where Y and Z is, but do you know where Q dash is? Do you see that? We know where Q dash is because it's parallel to Y. So that this vector which we are talking about, right? This vector is the same vector which is going to come here. And so if you just apply that in the reverse direction, I know where the point Q dash is. Okay. So even if I cannot construct XYZ, I can construct Q dash. And because of the what we already know, the parallel thing, right? This is a parallel ground, so this is parallel to this. So therefore, what is going to happen? These two lines are parallel. QZ and Q dash Y are parallel. So you obtained the point P. P is already given. With this transition, obtain Q dash. And now can you find point Y? Why can you? I am saying that you can find point Y. The reason is because what is the third thing that is fixed which we have not used so far? No, the angle, right? So this angle is fixed, but that angle is at X. Yeah, but we don't know that we what we have is P and Q dash. That angle is at point X. We don't know where the point X is. But isn't that angle equal to this angle? Because of parallel lines. So what is the construction we need to do now? On PQ dash, we construct the arc of that angle. Whatever is that angle, if you construct the arc, wherever it cuts RS, that will have to be 0.5. Right? So let me just illustrate this in a separate diagram. So like if I give this task to you that I'm going to give this circle. So this is what is given to me. I constructed this circle. I given points P and Q. I given points R and S. And separately on the side, I given you segment of density. and I have to find the position of the point X so that if I complete the diagram, that segment will be of length. So how will I proceed? First, what I will do is I will take parallel to RS, I will draw a line through this point Q. Okay? And on that line, with D as my distance, I will make an arc and I will get a point Q dash. Okay? So this D and Q dash are equal. And now I still don't know where X, Y, Z are, but based on that diagram, what we saw earlier, wherever the point Y is, can I be sure that wherever that point Y is, this angle PYQ dash will be equal to PXQ. And although I don't know where the point X is, do I know this angle? Because that angle is the same for any angle in this arc, right? I could take any point on the side, and if I join that, that will be the same angle. So I know the value of that angle, even if I know the position of the point X. So therefore, what can I do in my diagram? I just need to construct an arc on the segment PQ dash where that angle is getting formed. So what I can do is, for example, I just join. I take any point on this, okay, and I'll join this. Okay. And so that is the angle which we want to use. And so, do you know how the construction that with this angle, what is the arc on line PQ dash, which has that angle? You can construct that arc, right? Like for example, one way to do it is that if you look at the central angle, so if I call this angle X, then the central angle here will be 2x. So if I construct this isosceles triangle on segment PQ dash, such that here also the central angle is 2x. Okay. So I constructed this isosceles triangle on PQ dash, and let's let me call this point O. And so with O as the center, if I draw a circle, right? If I draw a circle with O as the center, like this, then you see any point on this circle, and if I join that, I will get an angle of X, right? With respect to PQ dash. So every point on this R is going to form an angle of X with respect to PQ dash. And in particular, look at this point. So this point is also going to form an R angle X. Right? So this angle is equal to X. Okay. And so what will happen now? This angle is X. So now if I extend this line and let it meet the original, that is also called X bracket. So now that point is my X, capital X. Why? Because what will happen now? If I join this point to Q, okay, so I join that point to Q, okay, then this is going to form a parallelogram. Because this is X, this is also X. So both, I have two sets of parallel lines. This is one set of parallel line, and this is another set of parallel lines. So this is going to form a parallelogram. And therefore, this segment Q dash Q, which was equal to D, will also be equal and parallel to this segment. And so therefore, the length of this segment is also going to be small. I have to rush to the proof little bit because we're out of time. But maybe we'll revise this next time before we start. But hopefully, if you understood the idea, you can try to do this construction on your own at home. But okay, so this was all about one congruence transformation called translation. Let me just mention the remaining transformation. So just like translation, we have rotation and deflection. So rotation is simply, as the word says, rotation, where you take an object and you rotate it around some axis. And reflection is you reflect it in some line. And together, all of these three together are called congruence. Because as it turns out, there is a theorem it says that if you take any two objects in the plane which are given to be congruent. So let me say that this triangle A1, B1, C1 is given to be congruent to some other triangle A2, B2, C2. Then through some combination of these operations, I can pick up this triangle and place it here. Like what can I do? I can first translate it. For example, what if I first translate it so that the point B1 coincides with B2? It's under that translation, I'll get a new triangle like. And then I will do suitable rotation so that this triangle coincides point by point. So some combination of these operations can always be used to take any congruent object in the plane to any other congruent object. That is the most important theorem in congruence. Okay, but we'll discuss all of that next time. That's all. Thank you. Bye.
Bye, sir. Thank you, sir.